Hello, everyone. Welcome to what will be pre-lecture 28. And this, we're going to go through the Nernst equation as well as calculating electrochemical cell potentials. So last class, we talked about electrochemical cells. In particular, what we're usually interested in are galvanic or voltaic cells, which are just the same thing. Just as a reminder, and they look like this, where we have two separate electrochemical half reactions, and our electrons flow through some sort of circuit that they're able to power, and then we balance our charge with our salt bridge. We also talked about how we have an anode and a cathode where our reduction and oxidation reactions take place. And so this pre-lecture and what we're going to talk about in class is then about how we can figure out actual potentials or voltages that are going to be associated with the development of these electrochemical cells. Okay, so generally speaking, we have to measure the electrochemical potential of a cell by taking the potential of the cathode half reaction and subtracting the potential of the anode half reaction. So anytime you see uppercase E, that is just going to be a measurement of potential in voltage or millivolts if it's very small. And so we have to compare these to something. And so our voltage is not an absolute value. And so we have to reference it to something. And so what we reference it to is typically called the standard hydrogen electrode, or SHE. And what it does for us is it sets our electrochemical potential scale to 0.00 volts. And what that electrochemical half cell is actually made up of is a platinum electrode, 1 molar solution of a strong acid, and then basically H2 gas that comes in at 1 atmosphere of pressure. So these are our standard conditions that we talk about. And again, when we meet all those criteria, we can measure a potential of 0 volts. Okay. So if we were to hook up a standard hydrogen electrode like this to another electrochemical half cell, then we can measure the standard reduction potential of that other half cell. And so, for example, here, because we know this half cell is 0, our copper reduction cell, if we have 1 molar copper solution, a copper electrode at 298 Kelvin, then we can measure a reduction potential, or a standard reduction potential, we would say, of 0.337 volts. And so that would be how we would actually measure these reduction potentials. So in your textbook, this is where this table comes from. We have a table of common standard reduction potentials for different elements. Something that I'll point out here is that by convention, we record the reduction reaction. So you'll notice that all of these reactions are some element plus electrons, and electrons thus are always on our reactant side. For our reduction reactions, they're never going to be on the products side. And the more positive the potential is, we would say the more oxidizing something is. So for example, fluorine gas turning into fluoride is the most oxidizing reaction in this table. And lithium ions turning into lithium metal, the bottom is going to be our most reducing potential. Okay. So species with more positive reduction potentials are more easily reduced, meaning that fluorine is very easily reduced, whereas species that are more negative tend to be very easily oxidized, meaning that something like lithium metal is very easily oxidized. Okay. So a potential question I might ask is something like, what is the cell potential for an electrodes made out of silver and barium? And what is oxidized and what is reduced? And so the way we would figure that out is that we would look at our table here, and we have standard reduction potentials for silver and barium. And so silver is shown here, barium is shown here. And what we want to do is figure out which one of these is more positive. And so in this case, silver is our more positive reduction potential. It's 0.7996, whereas barium is minus 2.912. And so what we want to do is, because our silver is more positive, that means if we think of electrochemical potential, the more positive it is, the more spontaneous it is. And so the more positive reaction is going to be favorable, whereas our more negative reaction is going to be less favorable. And so that means that our reduction reaction that is more positive is going to stay our reduction reaction. So our silver is going to stay the same potential, and that is going to be our cathode reaction, because a reminder, reduction takes place at our cathode. Then our barium reaction, we're actually going to flip that around because it is going to take place at our anode because it is more negative. And so that means we'll subtract the value that is listed here. And so we would do minus this 2.912 volts. And if we just calculate that, we get 3.711 volts, and that would be our electrochemical cell potential. Okay, and so for a spontaneous cell, so a galvanic or a voltaic cell, our E cell is always going to be positive. Okay. Something of note here is you do not multiply the reduction potential standard values by the number of electrons transferred in order to make coefficients balance. So for example, here with silver, we only transfer 1 electron. With barium, we transfer 2 electrons. We need to balance that out if we're balancing our electrochemical reaction like we did in class on Tuesday. But if we're just finding out the potential, we don't need to multiply our reduction potential values by any sort of coefficient, okay? All right, so time to tie it all together, what we've been talking about the last couple of chapters. And so our reduction potentials can actually be related to Gibbs free energy and equilibrium values, or Ks, because ultimately all of them are measuring the spontaneity of some sort of process. And so for electrochemical cells, we can use this equation here where E standard for the cell is equal to R times T over N, and being the number of electrons transferred, and F being Faraday's constant, shown here, times the natural log of K. And so that would be how we relate our equilibrium constant and our reduction cell potential. Then we can also do delta G standard is equal to negative N, and again, being number of electrons, F Faraday's constant, and then E cell, which is our electrochemical potential. So how we relate Gibbs free energy and our electrochemical cell potential, okay? If we tie them all together, we can actually make this neat triangle here where we have these equations that all go between our delta G standard, our K, and our E cell values. And just a reminder that for any sort of spontaneous reaction, K will always be greater than 1 if it's spontaneous. Delta G will always be negative if it's spontaneous. And our E cell standard value will always be positive if it's spontaneous. Okay. That's it for this pre-lecture. Hope it was helpful. If you have any questions, please let me know. Otherwise, I will see you in class.